everyone, and welcome to 10th lecture of Digital Elevation Models and Applications course. Those who have been going through the first 9 courses may realize that now we have reached to the mid mark of this course, and the topic is also very interesting, especially personally to me. I always enjoy studying shader relief models, generating shader relief models, and discussing shader relief models and their applications, which can be exploited to a large extent. The advantage with shader relief model, with the using simple digital elevation model or TIN, one can create a surface which can give a depth perception. So we don't have to resort to some sophisticated processing. A simple processing can enhance our presentations and can create shader relief models. We will see how people are exploiting these shader relief models for their usage. Also, there is another term which is used for shader relief model is hill shading. Like in ArcGIS software, they use the term instead of SRM, that is shader relief model, they use the hillshade. So don't get confused, both are the same thing. What basically hillshade or shader relief model is, that is a grayscale 3D representation of the surface. So within one frame, you get a depth perception with the sun's relative position, because here the sun position or illumination source and its elevation and azimuth can be chosen by the user itself. But by in default, it is always assumed that illumination source is coming from northwest direction. And therefore, in all the softwares, when you go for hill shading or shader relief model, like in ADAS or in NV or ER and ArcGIS, you would find that the values, the azimuth values are always written that they are coming from, the illumination source is in the northwest direction. But nonetheless, as per our requirement, we can change this sun's relative position, that means azimuth and elevation, and can create shaded relief models as per our requirements. We will see in the last few examples how we can play with these values. Shaded relief model or hillshade simulates the cast shadow thrown upon a raised relief map and more abstractly upon the planetary surface represented. That means that if the terrain is flat, then no matter how much illumination is coming and for whichever direction, there will not be any shadow. But if terrain is having undulations, ruggedness, then shadows will be created no matter again from which direction illumination source is coming. So the shader relief models, the effects of this hill shading processing can only be seen for a hilly terrain or rugged terrain. And the shadows normally follow the normal convention of top left lighting, that is the northwest direction, in which light source is placed near the upper left corner of the map. This is always assumed in case of, because when we discussed in the previous earlier lectures that if we put the this illumination source, say for example in southeast direction, and then what happens that the terrain will look inverted. So valleys will appear as ridges and vice versa. But if we keep the this illumination source in northwest direction, then we see incorrect perception, because the concept here is that if the viewer and the illumination source are in the same hemisphere, when we are illuminating from southeast direction, in that scenario, the viewer and the illumination source are in the both are in the southern hemisphere, and therefore you are bound to see a false topographic perception phenomena. But if a illumination source is in the opposite hemisphere, like when we are illuminating a surface from northwest direction and the viewer is in the southern hemisphere, then when these two are in different hemisphere, then we will not see false topographic perception phenomena. And that is why in default in most of the softwares it is assumed that illumination source is coming from northwest direction. If a map, because a map be orient always north upward. So, if a map is oriented with north at the top, the result is that the light appears to come from the northwest. This is always assumed, and based on that these default values have been kept in the different software. So, however, this unrealistic for maps because the sun does not shine from northwest direction. So, in real world scenario this never happens because before it reaches to the northwest direction it will set at the west. Therefore, the normal convention is followed to avoid this false topographic perception phenomena as I have just discussed. Hill shading is an effective technique to give a 2D map of terrain a 3D appearance. So, it is a quick way of creating a 3D perspective, not exactly what 3D perspective we use when we drap satellite images over a digital elevation model as discussed in previous lecture. But here we will see very soon some results of this shaded relief model or hill shading. So, this is generally achieved hill shading using a single point source of illumination. We will also see an examples how we can have varied source of illumination. So, not only illumination from one direction is possible, but nowadays we can illuminate the same terrain, same surface using multiple directions or rather 8 directions. So, here in this illustrations what we see that the sun is in the northwest direction and it is illuminating the surface or a terrain, and this becomes the azimuth. So, the azimuth angle will be measured in horizontal plane with reference to the north. So, this would be the azimuth angle, and this becomes the elevation angle with the normal here and with the this normal. So, this becomes the sun elevation angle. So, these angles, the two angles which we have to think while creating a shaded relief model or hillside. For DMs, the cosine of the angle between a surface normal vector, which is the surface normal vector representing the illumination direction, defines the gray values for each unit. So, this we have to remember when we interpret these shaded relief models. This is one example that suppose there are 8 facets are there. So, 8 sided hill shaded and this pyramid which we see here. So, if we are illuminating from northwest direction, then this facet or this triangle will be illuminated most, it will have maximum lighting, whereas in opposite direction, that is the southeast facet or triangle will have the darkness or shadow. So, this is what is done through a this convolution filtering technique. Like here, this is the input raster, and earlier like when slope and aspect we have used the same thing. So, here when a hillside is created, these are the values which are given for different directions. So, for different directions different values are assigned, and we see that how these undulations because of shadow they are highlighted. One thing again, because it is based on convolution filtering or spatial filtering we say, so on the edges we are having still problem, because on the edges we do not have the complete data, and therefore one row and one pixel on both top and left and right and bottom will have no output in case of hillside. And no data we have already discussed that here is one no data is there. So, for that also we will not have any output. So, hillside raster has an integer value range from between 0 to 255 because 8 bits can be created very easily, but depending on the requirements and softwares one can go for larger range. Instead of 0 to 255, one can go for 0 to 512 and so on. And the analysis of shadow is done by considering the effect of local horizon at each cell. and the raster cell in shadow are assigned a value 0. That means depicting the shadow. So, again the jet factor which we have discussed in case of slope and aspect calculations, same jet factor will play here important role. That means the xy scale and z scale has to be same. So, if it is not in our data is not in UTM projection, then we have to get a correct jet factor for that latitude areas, because with the varying latitude jet factor will also vary. So, these values can only be derived, the jet factor, correct jet factor value, in order to convert your z axis equivalent to xy axis or horizontal axis, a jet factor value has to be found out, and that can be determined using where exactly your study area is there. But if you convert to UTM projection using some GIS softwares, then jet factor, which is generally given in softwares as 1, can be used, because in that case your horizontal scale and vertical scale becomes same. So, jet factor is essential for correct calculation when the surface jet units are expressed in unit and different from the xy unit. So, this one has to always remember, and just in the default, normally in most of the software it is given 1. If you accept 1, and whereas these two your horizontal scale and vertical scale are different, you are bound to have wrong results. So, one has to take care about this. Now, hillside parameters, this is the primary factor when creating a hillside map for any particular location, is the location of the sun in the sky, from which direction you want the illumination should come. Normally, we have discussed, conventionally we have discussed that it is from northwest direction. So, this direction is we use the term azimuth, is the angular direction of the sun measured from north in clockwise direction between 0 to 360. An azimuth of 90 degree, that is east, and the default is 315, that is northwest direction. And similarly, for default sun azimuth direction for hillside is 315 degree, whereas altitude or sun elevation also we use a term sun elevation. This altitude is the slope or angle of illumination above the horizon. So, this altitude is measured in the vertical plane, whereas azimuth is measured in horizontal plane, and the units here in degrees from 0 on the horizon and 90 overhead. So, as we know that in the early morning the sun is at the 0 elevation, means it is just parallel to our earth or horizon, and we say sun is in horizon, and then by noon it reaches to overhead, and that time the elevation angle becomes 90 degree. Whereas the default values in most of the softwares you would find it is 45 degree. So, midway it is kept, whereas in case of azimuth the default value is 315. And this is what we are seeing here, that in case of sun azimuth this is always in the northwest direction, whereas in case of this sun elevation or altitude of the sun, it is 45 degree. Now, the example here which we will see that the azimuth is the same in each image, but the sun angle altitude has been modified, and these two examples are depicting that here when we have the low sun angle, means no low sun elevation in the morning or evening, when sun is near horizon, then shadows would be longer, and this is what it is depicting here. Whereas when sun is having high angle, elevation angle or overhead, you won't have any shadow at all in a perfect overhead scenario. But normally because you may not have sun depending on the season and where you are located, sometimes you may get, even at noon you may get some shadows. So, that is the example here given. So, it plays very important role, and at the end of this lecture we will see two simulated animations where these we can simulate and then animate through a film a short film and can see the effects of sun elevation and sun azimuth, how they play very important role in our perception of the terrain. Because after all, why we are creating a shaded relief model? Just to bring a depth perception in our surface, that is our digital elevation model. So, how exactly this is calculated? To calculate this shade value for each cell, the altitude and azimuth of illumination source are needed. So, which are provided by the user. Default values we have already discussed. These values will be processed with calculation for slope and aspect to determine the final hillside value for each cell in the output raster. And the algorithm for calculating the hillside values is like this, that hillside equal to 255, because as said that if in 8-bit scenario, this is what the value can be. But if it is not 8-bit, say it is a 16-bit or beyond that, then these values will change. And this is the algorithm which will be used, and here the angles are in radiation. This you are having zenith and then slope, zenith, radian, sine and slope, and then finally we get the hillside. So, note that if the calculation of hillside value is less than 0, the output will be equated to 0, because you cannot have a different illumination for that case. So, options, for example, if I take example of popular GIS software which one can use to create hillsides, like for example ArcGIS, then here is the example, and these are the details which are mentioned against the jet factor. So, when you go for option for hillside through toolbox in a spatial analyst extension of ArcGIS, you have to provide the input raster here, you have to provide where your output or the hillside will be stored, and as you can see the default values are already here. For the sun azimuth is 315 and altitude, that is sun elevation, is 45. You can, of course you can change these values, but generally. And do you want to model the shadows? That optional, that option is also available. Jet factor, though here it is mentioned optional, only when you are having horizontal scale and vertical scale are same, then only you can have jet factor 1, otherwise not. We will quickly go through this help file, which in case of ArcGIS is given, that number of ground XY units in one surface Z units. So, this is if it is the same both horizontal and vertical scales, then one jet factor can be used. Otherwise, the jet factor adjusts the units of measure for Z units when they are different from XY units of the input surface. The Z values of the input surface are multiplied by jet factor when calculating the final output surface. So, that has to be taken care about using any software. Default values will be there, default jet factor will be there, but we have to know very carefully that what we are going to do. I have been mentioning again and again, because this is the common mistake I have seen with the students while calculating either slope, aspect or hillsides. Whatever is given in default, they will just accept it and will create a product, which is going to be erroneous if you are having horizontal scale and vertical scale different. So, this care must be taken. Now, as I have said, so far what we have discussed, only the single directional hillsiding, but nowadays it is also possible to create multi-directional hillside, and we will also see the example and compare with single directional and multi-directional hillsiding. So, traditionally hillsides are created by illuminating light or putting the sun illumination source from northwest direction, and sometimes this often produces results in which illuminated sites are overexposed and terrain details or non-illuminated sites are obscured. So, if you are putting like in northwest direction, the slopes which are facing northwest direction are having very too much light, and whereas the slopes say for example opposite to northwest, that means the southeast direction, they go complete in shadow, and you lose details about both these surfaces, slopes facing northwest direction and slopes facing southeast direction. But in multidirectional hill shading, we can avoid these overexposed or underexposed surfaces or slopes. So this issue of over and under persist even more in areas with medium to high slopes. In highly rugged terrain, a single directional hill shading may not be very good, and that is why this thing has been developed. So this Bressel in 1974 recommended is setting a variable light source direction for each cell, that is the cell of a input digital elevation model, based on a primary direction plus minus a directional adjustment computed from the aspect of the cell. And Bressel also recommended that illumination inclination angle, that is the elevation angle, how the sun, high the sun is for each raster cell should be variable. So based on the deviation of the surface normal to primary illumination source. So you can have multiple azimuth as well as multiple sun elevation angle. And by Bressel's method, every cell could receive a hillshade based on a different illumination angle. And however, so far this has not been implemented. So exactly what he has proposed has not been implemented, but partly it has been implemented into GIS and digital image processing software. What it has been implemented, we will see, and also we will see the algorithm part as well as the results and then compare. So this is another contribution by Robert Marks, multidirectional oblique weighted method in 1992 has been implemented into GIS software. This MDAO method, the landscape is illuminated for 4 directions, each separated by 45 degree, covering an range of 135 degree. And by this method, the hillshade generated by each of these illumination source is then weighted according to the aspect of the cell. And here what we can see that starting on this x-axis we are having 0 to 360 degree, and this is the aspect derivation from illumination source, and here we are assigning the weight. So at 90 degree we are having maximum weight, whereas 180 degree we are having almost 0 weight, and at 270 degree again we are having maximum, and so on and so forth. So the cumulative effect will produce a hillshade illuminating generally from average of 4 illumination directions. And this graph below illustrates that shows the weighted of all 4 illumination sources based on the deviation of the cell's aspect value from the cumulative direction of illumination. So as we can see here that this blue, the source 1 is plus 67.5 degree. So here one illumination source, another illumination source as plus 22 degree. Here we are having third illumination source, it is minus 20 degree, because first we have decided that in this particular illustrations that effective primary direction of illumination is coming from west direction, and that is why these two values are in positive and these next two values are in negative. So ultimately we get 4 illumination source directions, 1, 2, 3 and 4. So 3 is minus 22.5, and then if we make this 22, it is say the 45 degree difference, and third illumination source and fourth again you are having minus 67.5 with reference to the primary direction of illumination. So these are the weighted factors which are assigned, and then illumination is created for a input digital elevation model. So by modeling shade, one calculates the local illumination and then and whether the cell falls in a shadow or not. And by modeling shadow, one identify each cell that will be in the shadow of another cell at a particular time of the day. And cells that are in shadow of another cell are coded 0, or all other cells are coded with integer values between 1 to 255. Again, 8-bit scenario. So, total variations we can have of 256, 0 is also included. And one can reclassify all these values which are greater than 1 to 1, producing a binary output raster as well. Example is here that here you are having multidirectional hillside, a soil map with a hillside, simple hillside. So, it is often useful to use a hillside raster to show terrain to support other information on a map. So, generally nowadays whenever if one has to show a lithological map or even point data, for example, locations of epicenters or locations of some observation belts or locations of some villages and other things. If in background if we are having a hillside, a conventional hillside, that will add to the information, and this becomes very useful to understand the terrain conditions along with the data as well. Here the examples are given that a simple digital elevation model which goes as one of the inputs and along with your sun elevation and azimuth angle and jet factor, and you can create a hillside by default you will create a hillside with black and white. But if I give a color palette to my original DM and make this DM say 50% transparent, then I can see below the presence of my hillside. And if I keep this arrangement that DM is having a color palette having a 50% transparency and in the background I am having hillside, then I will see a color hillside something like this. And if I have to show say a drainage network, it looks very convincing that how these can be represented very easily, and understanding of this becomes much easier. But without using hillside or colors, if I just overlay these drainage over this simple DM, I may not be able to convince the audience or people very easily. So, that is one of the advantages of hillsiding or shadow relief models. But this so far the example of single directional one. Another example here that very famous or one can say notorious San Andreas faults in California, which is in a very highly seismic active region of the world, and also one of the seismically active region of India is also shown, and in the background you are seeing the hillside. So, when we say plot the fault like here, we can depict all details and changes in topography and the corresponding changes in the topography very easily. So, that is why hillside are now being used in the background for creating some very interesting maps and very convincing maps also. Another example is in the background you are having hillside, a simple one directional hillside of Nepal, and where these earthquakes have occurred. This is the location of 12th May earthquakes of 7.3 magnitude, and top of this with a transparent layer, maybe 50% transparent layer of a deformation map derived from SAR interferometry of ALOS pulsar data. So, two data sets, one is in the background, another one is 50% transparent, but it is a deformation map, and this is what you can depict very easily, that whether there is a relationship with the ruggedness of the topography or not, that can be seen very easily if such products are generated, and these are very easy to generate. Another example is a 3D perspective view can also be created. Again, a deformation map has been draped over a shadow relief model, which is created using a already available digital elevation model of Kathmandu area, the first earthquake of 25th April, which occurred in near Kathmandu, and all we can see that this is the deformation maximum happened in case of Kathmandu Valley, whereas in other places also can be seen. And this is the comparison between a single directional hillsided and multidirectional hillsided. What is here, as you can see that lot many areas or the slopes which are facing southeast direction got completely in shadow, and not much details can be seen here. But when we create a multidirectional hill shading, keeping a primary direction, say from the best direction, two more directions from between north and west, and two more direction between west and south, then we are able to see more details about the slopes which are facing southeast direction, and overexposing is also not there. And that example you can see that here in the single directional hill shading, what we are seeing that these slopes have been overexposed, and therefore the details have disappeared. But if we go for multidirectional hill shading, then all these details are still visible here. So definitely multidirectional hill shading is very useful, becoming popular, and it has been implemented in many standard GIS softwares. So on the right side we are seeing the standard single directional hill shade, and whereas on the right side we see the multidirectional hill shade. And as we can see that multidirectional hill shade enhances the expressionless regions which otherwise were completely got overexposed and accentuated minor details in terrain as compared to the traditional single direction hill shade which is on the left side. So what are the advantages of multidirectional hill shading over single directional hill shading? We can realize that multidirectional hill shade presents an unparalleled view of the world's mountains, plateaus, valleys, canyons, and hilly terrain. And by varying the direction of the light, we can choose. It is not that primary direction has to be always from the best direction, but we can choose primary direction. But generally, in default, this is kept there. So by varying the direction of the light from four different sources or four different directions, terrain depicted by the multidirectional hill shade is more realistically represented by balancing the overexposed and underexposed or non-illuminated areas of the terrain or relief. And multidirectional hill shade enhances the expressionless regions and accentuates minor details in terrain as compared to traditional single directional hill shade. And by adding the hill shade layer to your map, no matter whatever the map is, maybe a soil map, maybe a lithological map, maybe a fault map, maybe earthquake epicenters, or maybe a deformation map, examples we have seen. If we bring this hill shade or maybe a multidirectional hill shade in the background and bring our map in a transparent manner, then it becomes provide a very clear context and increase locational understanding, terrain conditions about whatever the phenomena which we want to depict through such integrated maps. One example here is that in the background we are using a multidirectional hill shade, and these drainage network is shown, geological faults have been shown, because sometimes they are having a direct correlation with the ruggedness or alignments with the mountains and valleys. So if we plot both together and create such products, we can see things very easily and convincingly. So as we know that mountains or hilly areas where the relief undulations are there may look eternal, but in fact they have been saved over millions of years by the interplay between tectonic forces and water erosion. And therefore we try to plot all these things over a hillside so that we can convince the audience very easily. And this relationship becomes clear when the hillside is juxtaposed with rivers and faults, and we have just seen the example. And the hillside is especially useful when displaying a relief of mountainous regions. Of course, for flat areas, hillside may not be any use of us. And another example of this multidirectional and single directional hillside can be seen of a Mount Rainier in Washington, and this is what we see here, that many details about the terrain now can be seen in multidirectional hillside as compared to single directional or unidirectional hillshading is there. Another application of this, that land cover or land use map, land cover land use map has been overlaid over over a multidirectional hillside, and the top map, which is a land cover map, has been made transparent, maybe 50% or 40% depending upon of the terrain conditions. And then both things you are seeing in such products, integrated products, not only you are seeing land covers, but you are seeing the relief and topography as well. So one can even checks the quality of the output of land cover when we integrate such maps. And also in glacier studies, one example, or in avalanche studies, these can be used. One example is here with multidirectional hillside, and over which these glaciers have been plotted. That layer has been juxtaposed over this. Multidirectional hillside is another example from India, and what you see here in the background is this ester GDM of 30-meter resolution, and then you see this Shivalik ranges, then Doon Valley, and then you are seeing lower Himalaya and higher Himalaya as well. One of the examples or one of the uses of hillsiding also discussed in earlier lectures when I elaborated on false topographic perception phenomena, that if we want to remove the false topographic perception phenomena, or in short FTPP, from satellite images, then when we can create a opposite direction, directional hillside, which is opposite to the satellite image illumination source, and especially the azimuth, because generally in sun synchronous or polar orbiting satellites, when the data is acquired, the sun is generally in the southeast quadrant. As we can see, it is 163 degrees, the sun azimuth angle. So if we want to remove the FTPP, because here in this example the river is flowing on the ridge, that means it is suffering, the image is suffering from false topographic perception phenomena. And if we want to keep north upward and would like to get rid of FTPP, then we can create first a opposite directional hillside like here. So 163 plus 183, we get a 343 degree for sun azimuth, which is just opposite, and in which we can see that the river is flowing in the valley. That means in this simulated image, the FTPP has gone. Now this image can be used through color transformations to get an image which will still have north upward, and FTPP is gone. Color transformations, in color transformation what we do, we use the hue and saturation of the original image, like in this one is this left image, and intensity part we use from this simulated image, and then we can create a product in which north is upward and FTPP is gone. So just using a simple concept of hillsiding, we can get rid of a very complex phenomena which is FTPP. One more example is here. This is simple digital elevation model. This is a hillsiding, so we can consider as intensity image, and when we do color transformation using the colors and saturations of this input image, then when we can create a product in which the FTPP is gone. Two examples of animations, which is simulated animations, I will show, and I have also shown in previous lectures as well, previous lecture, that here 8 hillsidings of different directions have been used to illustrate or to explain how FTPP affects. So when sun illumination or azimuth is in the southern hemisphere, then FTPP is seen in a satellite image, in this, like in this particular example. And when sun azimuth is in the northern hemisphere, viewer is always assumed to be in southern hemisphere, that is, in both are in opposite direction, then FTPP is gone. So when you will see that this is the sun, when it moves in the northern hemisphere, and then we do not see FTPP and a river appears to be in the valley. But when it comes in the southern hemisphere, that means the viewer and illumination source in the same hemisphere, we are bound to see FTPP. So, this in simulated animation illustrate that. Another example is not playing now with the sun azimuth, but instead playing with the sun elevation angle. And in this example, we see that when the sun is near horizon, the darkest image which you see at 5 degree. So, when the sun is at near horizon, and then you are having the maximum darkness in the image, because the shadows are much larger for the same slopes. But when sun is overhead, then you see the terrain is very bright and your shadows are very small. Also it varies, this sun elevation angle can also change our depth perception as well. So, when you are having large shadows, we feel a higher depth with the or higher ruggedness in the terrain, but when the sun is overhead or 90 degree, then we see the less. So, this also illustrates this one. So, these two angles, sun azimuth and sun elevation, are very, very important angles to simulate or create a terrain surface using digital elevation model as hillside or shaded relief model. So, this brings to the end of this discussion. Thank you very much.